Okay, thank you. So I'm Yannis from Dedaub. I'm a co-founder of Dedaub. So I'm going to talk about vulnerabilities and stories from the Auditing Trenches. I'll try to give a couple of technical tidbits. I cannot give too many anecdotes in 16 minutes, but I'll try to show you code in at least 2 occasions. Now, we're Dedaub. If you know us, probably you know us from Contract Library, which is probably the best decompiler for EVM bytecode. So it's a security-oriented explorer for contracts, so many hundreds of people use it every day. Primarily, we are a company that does research and develops technology in program analysis, especially static analysis, and applies this to multiple problems in smart contracts. Maybe some of you have used library.dedaub.com, our contract library. So that's our most used service. And we're also an auditor for many top protocols. So we've worked with several prominent clients in the space. So we've done more than 200 audits. I will define what an audit is exactly, because why am I saying 200? Why am I not saying 500 or something? So we'll talk about that a little later. And we've also found lots of vulnerabilities in the wild. So very quickly, maybe are some stories that you may have seen about us, but we've gotten several bug bounties in the past couple of years. It says 10 there, it's probably 12 right now, but gotten many vulnerabilities in the wild disclosed. So with this introduction, let me try to get to a couple of technical tidbits. One is introductory, the other will go into things that I like to talk about when we're doing audits. Technical tidbit number 1, I can't not present this. Phantom functions. It's the source of our largest vulnerability in the wild to date. It was a hack. It was a white hat hack. It would have been a hack for more than $1 billion if perpetrated, if we hadn't disclosed that. And if you have not seen it, it's really, really cute because that's all the buggy code. Everything you see here is the buggy code, period, nothing else. And it's also very cute because the 2 functions that I'm showing on their own are perfectly fine. Both the top function, the deposit, and the bottom function, the deposit with permit, on their own are perfectly fine. And I don't have a pointer, so you'll have to imagine I'm pointing somewhere. So what does this code do? It's a generic code that handles any token. It was a bridge in this particular case. And it does 2 things. Function deposit at the top says, if you've given me an approval, if you've given the bridge an approval to spend your tokens, and you're also the caller, then I can transfer your tokens. And this is perfectly fine, because I'm the caller. I've authorized this. And deposit with permit below, you may be familiar with the ERC20 non-standard, but almost standard for most tokens permit function. That's a way to offer permission, not with an approve, but with off-chain signatures. So deposit with permit says, if you give me a cryptographic signature, those VRS arguments, and that proves that someone has signed an approval for spending their tokens, then I can take anyone's tokens as long as they are the signers of this cryptographic message. And that's also perfectly fine. The bottom part, the deposit with permit, on its own would have been perfectly safe. Now, perfectly safe, yeah, there is a caveat there, but it would have been safe on its own. So what's the issue here? The issue hinges on this question. This is very general code for any token. What's the phantom function? What's the permit function for WETH, for wrapped ether, the most popular ERC20 token? And the answer is it doesn't have one. So when I call permit on it, what will it do? Well, this is what it will do. It will call the fallback function, which in earlier versions of Solidity was the default function to get called when no other function selector matches. So it will basically make this permit a no-op. So getting back to our code, for WETH, calling permit is a no-op. That's what we call a phantom function. Phantom function is general terminology we introduced. It's a function that the contract does not explicitly implement, but it responds to without reverting. So getting back to our example, the bottom code, the deposit with permit, the first line, token.permit, is a no-op for WETH. It doesn't do anything. Okay, well then you're trying to transfer someone's token, but you don't have approval for that. The permit didn't do anything, so that's perfectly fine, right? No, it's not perfectly fine because of the many thousands of approvers that have approved the bridge because they're calling the top function. Top function on its own, perfectly safe. You transfer my money, I'm the message sender. Bottom function would have been on its own perfectly safe because permit doesn't do anything in this case. So no permission, but thousands of people have given permissions because they happen to call the top function in the past. So that's the phantom function vulnerability. Again, could not show this. It's very cute. We want the entire community to know about that. So getting to now the main part of my presentation, I'll try to offer a couple of tidbits from audits, and there's an endless stream of anecdotes from audits and interesting things in code. But actually, I cannot go through too much of that, so I'll try to stay at very high level generic lessons, but we'll still see some code. So we've done a total of over 200 total audits. Let's say in the past year, we've done about 60 audits or so. We're not counting re-audits. Anything that has a standalone audit report, I will call an audit. Anything that just adds to that, I will not. So I could give you statistics. I've seen other people give statistics, such as 35% of our audits report critical vulnerabilities. That's true. That's an accurate number for us. But I'm not sure that this means something. Actually, I think it's really good for an auditor sometimes to downplay severity, not at the critical level, but perhaps at other levels. So, for instance, our latest audit that also had a different auditor, we rated one severity low. This was our highest. The other auditor rated it high, and we gave several advisories that the other auditor rated low. So it's kind of subjective. What's the severity in some cases? Perhaps other than critical, although we saw examples even yesterday where people said, well, we had a critical finding, but it was totally dismissed. They said the context does not make it a vulnerability at all. But in any case, I don't want to give statistics on severity because these are highly subjective, and I think I should caution you to interpret statistics on severity very, very carefully. What it means can be entirely subjective. So we found, obviously, all kinds of issues when we inspect code. There are many protocol-level threats, many things that are completely domain-specific, price manipulation, lots of ways to game the system. There are obviously system-level threats. There's denial of service. There's front-running. Those are generic attack vectors, Sybil attacks, all sorts of things like that. And then you can find pretty severe vulnerabilities at the very, very low level. At the code level, something tiny, a logic error, some obviously reentrancies, the best known vulnerability in this space, rounding errors, overflows, all sorts of things like that could be gameable, could lead to a severe vulnerability. So we've missed some things, or we've given some bad recommendations sometimes, but not very often. I'm very happy to say we haven't been hacked yet. It's not a huge number of audits, but we haven't been hacked, so that's good. So we've had a few regrets, but too few to mention, as the song goes. And I will try to give an example of something that's of broad interest as a code example here. As a community of developers, we often say that we have upgradability in our contracts. So the original understanding at first when someone comes in the space is contracts are immutable. Oh, no, they're not immutable because they're upgradability patterns. And we have the standard upgradability pattern of a proxy and implementation, and you've used perhaps OpenZeppelin libraries, and you know that they have an entire parallel library version that's the upgradable version of all the contracts, and the contracts have gaps in their storage, so that even when more storage variables get added, the contracts can still function as deployed originally. and you can just upgrade contracts in place. Everyone here has seen upgradable contracts? Let me see a show of hands. Who has seen upgradable contracts? Okay, excellent. Thank you. So you know that the storage layout, the ordering, the exact sequence of on-chain state variables has to stay the same, and we have conventions to get this right, and upgradable generic libs is how most people use these conventions. Now, my take-home message is we don't have upgradability with this simple pattern. Maybe if you have something a lot more complex, you can argue that there's upgradability, but really, that's a wrong term. We shouldn't call it upgradability. It's at best patchability. So let me try to explain. This is one of our audits of the past 3 months. This comes from an audit, a recent audit. It's an inheritance hierarchy for a tiny audited project. So it was 200, 250 lines, something like that. I've renamed everything that has an underscore, that's underlined. So all the underlined contracts have false names. Everything else is a true name. This is an inheritance hierarchy for contract X. So contract X inherits from Y. That's also the client. Everything else is generic from libraries, and the inheritance hierarchy continues like this. So that's 200 lines of code that inherits from a whole bunch of reusable libraries, a great practice. All of them upgradable, right? Is it really upgradable? Can I deploy the next version and replace the code as deployed on that specific address? And the answer for most upgradable scenarios is no. And we should be very aware of that, and I haven't seen this mentioned too often. So in this entire complex hierarchy, if I go and I add a single contract anywhere, more likely than not, I'm breaking your upgradability because I'm breaking the linearization of all the super contracts. And I could be kind of careful and put it at the very end of my inheritance hierarchy for X. Doesn't guarantee anything. The linearization algorithm will go and find the first time some super contract is being mentioned anywhere on top. I can break this trivially. So we have upgradable contracts, but in practice, if I want to really change anything, I cannot. And not only we as developers, but also OpenZeppelin cannot. So even the library cannot go and change any of this inheritance hierarchy and maintain the storage layout. So this is very hard to get right, and it's a standard warning when people are trying to combine aggressive upgradability. They really expect that they will have a version 2 that they will develop for like a year, and then they will replace the original contracts. And at the same time, they use complex inheritance hierarchies, and perhaps not even themselves. They actually inherit from a library that inherits a ton of stuff. And think a bit about it from the perspective of the library designer. Libraries have to keep the same inheritance hierarchies because they otherwise break upgradability, but that's kind of insane, because we use libraries for information hiding. So now OpenZeppelin cannot just hide behind a name such as ERC 777 upgradable. They have to maintain the current super contracts of all that in their exact sequence. That's insanity. So getting back to my point, we do not really have upgradability here. At best, we have patchability, and this is a pet peeve. We actually mention this in audits, especially if we see the client try to have a real policy of upgradability in the next version. They probably need a more complicated pattern, which is also not a good idea for various other reasons. You've heard negative things about the diamond pattern, etc. So this gets to the end of my material. I had a few more slides, but I think it's very hard to try to get to unhide slides. So I'll go on with what I would have said in the extra slides, since I have a minute and a half. So the main lesson that I try to promote as an auditor when we're auditing a project is that we are not the owners of your project. You are the owner of your code. So you're primarily responsible as a developer for what goes on. what's the role of an auditor? The auditor is probably your best ally to come in, take a critical look, and try to advise. But your responsibility is to get one piece of feedback and turn it into 15. So your responsibility as a developer is you see a warning about a vulnerability. You think, well, is this really indicating that I have thought about something a little bit wrong and I can generalize it to perhaps 5 or 10 different vulnerabilities? That's the thing. So the worst client for us as an auditor is someone who says, all I want is the check mark. Give me the check mark. My project is safe. I just want to move on. So instead of that, we want, please have a critical look at the security of my project. Tell me what you see that might be wrong, and let me think now of what else I may have missed. So that's the best interaction that we as auditors can have with developers, and that takes a lot of communication, and that's what we strive to also do every time we audit the project, to have a good open communication channel and have two-way feedback. So that's all I have to say. Yannis from Dedaub. If you're not using Contract Library, please visit Contract Library and check out our decompiler. Thank you.